We're going to start off our discussion of pre-calculus looking at functions. Functions are a very fundamental part of algebra and trigonometry, and so we're going to start there. This is a very definition-heavy video because we're going to talk about different aspects of functions and get some terminology down. It's very important for you to understand the definitions I'm about to show you because I'm going to use these phrases and terms throughout the semester, and it's going to be important for you to know them and be very familiar with them. Hopefully this will become just a regular part of your vocabulary as we move through this semester. So we're going to start with the idea of functions. Now, functions are a type of relation. So let's talk about relations first. A relation is where you have a set of values that are related to another set of values. Okay, so we often think of like an x and a y relationship, two variables. You might have something like y equals 2x minus 3. That's a relation. It doesn't have to be an equation. It could just be any. This is a mathematical relation. But it could be anything. It could be, I don't know, the students in a class and their grade at the end of the semester. That's a relation. You have some sort of relationship between two aspects, the people and their grade, or a person's height versus their shoe size, for instance. That's a relation. I don't know. There's lots of different things that show up as relations. They could be numerical relations, like how much a person makes in their income versus how much they pay in their taxes. That's a relation. Okay, those are numerical relations, and they can be things like equations or graphs or lots of different ways to represent relations. Now, a relation, generally, when we talk about these in mathematics, we're generally going to be looking at relations that have inputs and outputs. You plug in a number, you get out a number. I think of it like a vending machine. You go down to the vending machine, you put in some money, and you get out pop, right? Or you put in some money, you get out a candy bar, something like that. And so there's an input and an output from that machine. A function is a mathematical machine that does something similar. Backing up, talk about relations for a moment. So a relation is a set of ordered pairs. It's the pair of things that are related. They could be numbers, they could be, like I said, they could be people and grade, something like that. So, or height and shoe size, any of that stuff. The relation, the set of all those pairs of things. Okay, so a relation is a set of ordered pairs. Okay, ordered pairs are things that are, it's a pair of numbers that are ordered. There's an input and an output. There's a person and their grade. There's a height and a shoe size. There's an income and a tax amount. Those sorts of things. And so a relation is a set of ordered pairs. So it's all of those ordered pairs that represent or that fall into the category. So if we're looking at students in a pre-calculus class and their grade, if we have 25 students in this class, then we've got 25 ordered pairs. It's each student with their associated final grade. Okay, so there's 25 ordered pairs. On an equation like this, y equals 2x minus 3, there's an infinite number of ordered pairs. For every number you plug in, you get another number out, and the pair of those two numbers is an ordered pair. For instance, if I were to plug in an x value of 2, plug in a 2, then I would get a y value that is equal to, well, 2 times 2 minus 3. 4 minus 3 is 1. And so the ordered pair is the pair 2, 1. Okay, so an ordered pair is just the combination of the input and the output. The set of ordered pairs is all of the possible combinations that you can have for that given relation. Okay. Now, a function is a specific type of relation. A function is a relation in which, and here's the important part, each input corresponds to exactly one output. Okay, so that's the key. Each input corresponds to exactly one output. Okay, so no matter what you plug into the function, you know with certainty you're only going to get one thing out. You can't possibly get two or more. Okay, you can't be guessing at, am I going to get this option or this option? Okay, every input, you're guaranteed a single output. I think of it back to the vending machine example. When you put in your money and you press you press a code or whatever, B3, and that gives you a bag of chips or a candy bar or something. When you press that code, the B3, you're not guessing at, well, maybe I'll get chips, maybe I'll get a candy bar, maybe I'll get gum, I'm not really sure. You know with certainty there's only one thing that's going to come out. Now it's a vending machine, maybe nothing comes out because it gets stuck, but you get the point. There's not multiple things that could come out, there's only one thing that will come out. Okay, so if I want a bag of chips and I press the code for that bag of chips, I know something else isn't going to come out. I know exactly what's coming out. That's a function. In the case of in the case of this equation here, 2x minus 3, I know that every number I plug in, no matter what it is, when I multiply by 2, there's only one output from that, right? No matter what I plug in, there's only one possible thing, there's only one possible number that's double that. Then when I subtract 3, I know there's only one possible outcome from that. So if I plug in a 5, I know there's only one number that's 2 times 5, and I know there's only one number that's that minus 3. And so at the end, I know there's only one possible output. Just like here, when I plug in a 2, I know 2 times 2 is, well, 4. It's not 4 or 6 or something else. It's just 4. When you subtract 3, I know it's just 1. There's only one possible result from that. Okay? In the case of, grades, students' grades, each person gets to the end of the semester and has a single grade. I would never take a class and say, I got to the end of the semester and say, oh, I got a B and a C in that class. No. Or B or a C. I only get one of the two, right? I get to the end of the class, I say, I got a B in the class. It's only one possible grade, or one actual grade, I should say. Now it is possible that in a class of, say, 25 people, you have 3 or 4 people that all have the same grade. That's okay. So if you have 5 people that all get A's, or 6 people that all get F's, that's all right, as long as each person had a single grade at the end. Okay, so Jeremy gets an A, and Alicia gets an F, and Tristan gets a C, and Sarah gets a A minus. You have all these relationships here, and so multiple people can get the same grade, but you can't have a single person getting more than one grade. Okay, so that's the idea of a function. Okay, so function, really important that each input corresponds to exactly one output. It's a very specific type of function, or of relation. Now relations in general can have, they can have lots of different things. You could have in a relation multiple outputs from the same input. That's okay. But in a function, you can't. And functions are primarily what we're going to study in this course. With some exceptions, we'll talk about conic sections later on in the class, circles and ellipses and hyperbolas. Where we don't have functions, we have relations. And we'll talk about those. They're very special relations too, ones that are pretty easy to work with. But functions are going to be our primary focus. Now, the inputs are very important. They create a set called the domain. We say that the domain is the set of all inputs. Okay, all of the inputs. So if I take, if I'm looking at the grades in a class, let's say this pre-calculus class, then if I take, the 25 students in the class with their 25 corresponding grades, the domain is the list of all students in the class. It's like my course roster. That would be the domain of the function. The range is going to be the set of all outputs. Those would be like all the grades in the class. Okay, so the range is the set of all outputs. Okay, so the range is the set of all outputs. So the domain is like everything you could plug in for x. These are like your x values. And the range is everything you could get out for y. So these would be like your y values. We often use x and y as those two variables respectively, the x for the inputs, the y's for the outputs. It doesn't have to be, you could change it up. If I was looking at income versus how much I get taxed, how much I make versus how much I get taxed, the amount that I get taxed is dependent upon the income, and so my income, maybe I call that I instead of x, and maybe the amount I get taxed is t instead of y. So I might change the variables up to match a situation, but generally speaking, we use x and y for the inputs and outputs respectively. We also have different names for these in inputs and outputs. I like to use inputs and outputs. It's just simple. Doesn't seem to be too confusing. But we also use the term independent variable. The independent variable is essentially your input. Okay, it's your x value. It's what you choose when you plug it into the function. The dependent variable is what you get out. That's your output. Okay, so the dependent variable depends upon what you plug in for the independent variable. That's why it's called the dependent and the independent variable. In the example of, what's the one I was just thinking of? The income and the tax. How much you get taxed. Well, how much you get taxed is dependent upon how much you make. And so what you make is the independent variable. How much you get taxed is the dependent variable because it depends upon the independent variable. Okay, that's where those names come from. That's why they are that way. And I always just remember that the independent comes from the input. The ends go together, right? And so that just helps me to personally remember the two. Okay, so that gives us, just a few quick definitions here. We also should look at how to find domains. Okay, domains are going to be very important to find. And now I'm going to start to really focus in on functions that are mathematical in nature, mainly equations. And then, we can always go back to talking about other types of functions like the students and their grades, that sort of thing. It's not really a mathematical type of function in the sense of like using numbers and equations. So I'm not going to go into a lot of those from here on out. But they still apply. Everything we're going to talk about still applies to those types of functions as well. Right? So, in this example, y equals 2x minus 3, the inputs could be anything. There's no restriction to what you can plug in here. I could plug any number on the entire number line, real number line, from negative infinity to infinity. I could plug in for x, and I know that no matter what number I plug in, I can always double it, and I can always subtract 3. Okay? Never going to have an issue with that. Okay, it could be a really small number, really big number, decimal, fraction, negative, a positive, 0. It doesn't matter what I plug in. I know I'm always going to be able to double it, always going to be able to subtract 3. And so there is no restriction here. That means that the domain is all real numbers. Now, all real numbers can be represented in 2 different ways, generally speaking. One of them, one I tend to use most often, is the interval notation from negative infinity to infinity. Of course, that represents the entire number line. Or we could represent it with a capital bold-faced R. We kind of use these 2 lines on the vertical part to make it bold. But this symbol is represents the real number set, the set of all real numbers, the whole real number line. So you can use either of these notations. I think a lot of times on my math lab it tends to want this notation. It's for whatever reason it likes that better usually, but you might see the other notation as well. So they're interchangeable, they mean the same thing. And this is the case whenever there is no restriction on the inputs. There's nothing that you can't use. So this means there is no restriction. I can't write. C-T-I-O-N, restriction on the inputs. Okay? No restriction at all. There's no restriction to what you can get out from this function either. So you can get out positives, you can get out negatives, you could get out decimals, fractions, whole numbers. Doesn't matter, big numbers, small numbers, everything in between. It all depends upon what you plug in, but there's no real restriction to what you get out. Whatever you plug in, what you get out is just twice that minus 3. Okay, so you could really have just about anything, or actually anything, out from this function. So again, there's no restriction, so our range is also the set of all real numbers from negative infinity to infinity. There's no restriction there. Now, where we find restrictions or problems, and we're going to focus really in on the domains here. The ranges are a little bit harder. The ranges depend upon the type of function we're dealing with, and they're found in many different ways. So I'm not really going to talk about ranges yet. As we move further into the course, we'll talk about different polynomial functions, linear functions, all these different types of functions, logarithmic functions, trig functions. They all have their own way of finding ranges for them, and we'll discuss those when we get there. Domains, I think, are a little bit more general. The general idea is you can use any number for a domain unless the result when you put it in is something undefined or something not real. Okay, I'll give you some examples. What are some things that could make undefined values? Well, division by 0 is a very popular one. That's a big one. So if I had a function like y equals 2x over x minus 5, then what would be a value I can't plug in here? Well, 5 would be. Because if I plug in 5, right, if x is equal to 5, then I get y equals 2 times 5 over 5 minus 5. Well, what's that? 10 over 0? Division by 0 is undefined. There is no such number that is equal to 10 divided by 0. Right? So this is undefined. And so when that's the case, if there is no output for a given input, that input is not in the domain of the function. Okay, so I would say that 5 is not in the domain. Okay, not in the domain. Is there anything else? I guess that's the other question. Is there anything else? Well, in this function, there's nothing else that will make the bottom 0. 5 is the only thing, right? 5 minus 5 is 0. Nothing else minus 5 is going to be 0. So there is no other problematic value. And so the domain is all real numbers except 5. Everything except 5. Okay? 5 can't be used. Everything else is fine. You want to use 4, good. 4 you can plug in, you get an output. If you want to put 6 in, 6 is good. 2 times 6 is 12. 6 minus 5 is 1. 12 over 1 is 12. Don't have a problem with that. You could plug in 1,000. You could plug in negative, 15 million. Doesn't matter. The only thing that's a problem is 5. Where did I put it? Right there. 5. That's a problem. Okay? Now, there's many different ways to represent this. All real numbers except 5. I would take this sentence, but it's not the most convenient. I would say the interval, if you think about an interval on a number line, if you have the number 5 here, what's all real numbers except 5? Well, it's everything to the left and everything to the right, but not 5. So it's going to be everything shaded to the left. It's going to be everything shaded to the right, but 5 is left unshaded. And so you're looking at two different intervals. You're looking at one on the left from negative infinity to 5, and you're looking at the one on the right from 5 to infinity. That's everything less than 5, everything greater than 5. Whoops. And I'm going to use a union symbol to represent that both of them are included in this set. Okay? So the domain is all real numbers except 5, so it's everything less than 5, right? Negative infinity to 5. Everything greater than 5 is 5 to infinity, but not 5 itself, so I have parentheses on the 5. All right? Another way to write this, and actually this is my preferred way, is in set form. Set form would say the domain is always x's, right? At least in this case, the domain is x's, so I'm going to put x in there such that x is not equal to 5. Remember, in set form, hopefully this is something you're familiar with, but I'll just refresh your memory or jog your memory here. In set builder form, you have the set braces on each side. You have this vertical bar in the middle, which separates the elements of the set from a property that they all share. Okay? So on the left, you have the elements or a variable or some way to represent them. We usually use x for the domain and y for the range, but whatever the variables are there. And then a property. Well, this is, as long as x is not equal to 5, it's going to be in that set. Okay? So x is a real number not equal to 5. That's going to be my elements and their property that they share. Okay, they're all numbers that are not equal to 5. Okay, and that should be a good domain for that one. There are many other types of functions that have problems, right? It doesn't have to just be a 0 in the denominator, although that's a very important and common one. You may also see square roots. Hopefully you guys know that taking the square root of a negative number results in an imaginary number, right? Or a complex number. And so if you have a square root like x plus 2, square root of x plus 2, well, there are certain things you cannot plug in here. I couldn't plug in a negative 10 because negative 10 plus 2 is negative 8, and the square root of negative 8 is a complex number. I'm not worried about complex numbers right now. There is going to be a time when we get into polynomial functions, we're going to deal with some complex numbers. But for right now, we don't want complex numbers. We're dealing with real numbers. And so we need the radicand to be greater than or equal to 0. Now the radicand, what the heck did I just write there? Radicand. Radicand is what's under the radical. Okay? That's the technical term for it. X plus 2 is called the radicand. All right? So we need that radicand to be greater than or equal to 0. So if we find the domain, then we take x plus 2, set it greater than or equal to 0. We know it cannot be negative. If it's negative, Square root of a negative is imaginary. It's not real, so we can't use it. So we want x plus 2 greater than or equal to 0. Subtract our 2 from both sides, and obviously you get x greater than or equal to negative 2. Now, again, this could be written in two different ways. You could have the interval form, which is just all numbers from negative 2 to infinity, everything greater than or equal to negative 2. And notice the bracket on the negative 2 means you include that endpoint. And then you could also have the set form, like we had a moment ago. We're going to have our braces on each side. X is the variable. The property that it has is going to be just this inequality. X is greater than or equal to negative 2. Okay, so we have our interval form and our set form for that domain. All right. As we move throughout the course, you're going to find other types of restrictions on functions. Logarithmic functions will also have a restriction similar to this, except they can't be 0 either. They can't be negative or 0, the inputs. And so logarithmic functions are going to be similar to this. Let's see, some of our trig functions, they're going to be very different, but there are going to be restrictions to what we can do with trig functions. So keep, just be aware of that as we move through the course. The techniques for finding a domain might change based upon the function, but the concept is this: you want to exclude any numbers that make for an undefined or non-real value. Okay, you exclude those things. Okay. Now I should talk about function notation for a moment. Function notation is very important. Go back to that first example I had where y equals 2x minus 3. We have a notation that nicely relates the inputs to the outputs. That notation is called the f of x notation. We generally use the letter f for this because it stands for function. It's a function of x. However, you could use g of x or h of x or c of x or anything you wanted to, depending upon the situation. So in this case, I'm going to write f of x equals 2x minus 3. Now, why is this useful? Because it nicely relates the inputs and the outputs. For instance, if I wanted to find the output when the input is 2, which I did earlier, it ended up being 1, I would write f of 2. 2 is what you plug in. That's why it's in the parentheses. You're plugging it in. And then you replace the variable with that number, the input, do the calculation, and 2 times 2 is 4, 4 minus 3 is 1, answer is 1. And so you have this notation now that in one line expresses both the input and the output. And you don't have to have like x equals blah and y equals blah. You don't have to have all this other stuff. It's just one nice line, has everything nice and tidy. When we did the example a moment ago with y equals 2x over x minus 5, if I change that to function notation, then I could more easily represent plugging things in and getting things out. Of course, I wouldn't plug in 5 because 5 doesn't work, but I could plug in anything else. Like if I want to plug in 6, right? I get 2 times 6 over 6 minus 5. That's 12 over 1, which is 12. And here I have the input and the output immediately accessible to me. I could even put them in an ordered pair very quickly if I needed to. Okay? Over here, the corresponding ordered pair, and we already saw this, is 2, 1. Right? So again, the inputs represent numbers in the domain. If you want to find the domain, it's a set of all the possible inputs, all the possible x values from the ordered pairs. If you had a list of ordered pairs, you just pick out all of the x values and write them in a list, right? That would be the domain. The range, similarly, is the y values. 12 is in the range of this red function here. 1 is in the range of the green function, but they're not the only numbers. There's lots of numbers in the range for those functions. And to list them out would be maybe a little bit exhausting, right? There's actually an infinite number of things in the range here. And so we have other ways to represent those, like sets and intervals. One very important aspect of functions is that you should always be able to write a function in terms of y. You should always be able to solve for y and have a nice equation with only one possible output as a result. Now, there are some relations that you can solve for y very nicely, and others you can't. Let me show you some examples. You could have a function like, I don't know, maybe x, y plus x squared y equals 5. And I say, okay, can I solve that for y? Can I get y by itself? Well, the answer is yes. To do that, I'm going to factor out a y. I'm going to pull a y out of this side of the equation, right? So there's a common factor of y. If I pull that out, it's kind of like the distributive property in reverse. Instead of distributing something into parentheses, I'm pulling it out. And that's going to give me an x plus x squared in the parentheses. Okay? So I've got y times x squared. That gives me the two terms on top. So if you imagine doing the distributive property, that would reverse this and go back to the beginning. To solve for this y, I'd have to divide out the quantity in parentheses because it's being multiplied here. So I'd have to divide out x plus x squared on both sides of this equation. Don't really need the parentheses there. That cancels out the entire set of parentheses on the left side. And on the right side, I'm left with y equals 5 over x plus x squared. Now this is a function. No matter what I plug in, if I were to, let's see, yeah, no matter what I plug in, there's no way to get two possible outputs, or two outputs, or more. You're only going to get one output. Why is that? Because no matter what I plug in for x, there's only one number that I would get when I square it. There's only one number that I would get when I add it back to itself. And then there's only one number I get when I divide 5 by that result. Those are, there's only one possible number you can get as an output from each of those operations. And so this is a function. This is a function. Now the domain of this function can be found by setting the bottom equal to 0, right? Because you can't have a denominator equal to 0. So to find the domain, I would take the bottom, set it equal to 0, and solve for x. Any values of x that make that 0 are going to be excluded from the domain. So here, how would I solve this? Well, it's a polynomial equation. Hopefully you've seen the technique of factoring to solve. If you think about, if I factor this out, they have a common factor of x. If I pull out an x, I get 1 plus x left over, right? And again, imagine redistributing this to go backwards. X times 1 is x times x is x squared. Okay, and there's a property in mathematics called the zero factor property. It says, or zero product property depending upon your textbook. It basically says that when you have two things multiplied together and they equal 0, a product that equals 0, at least one of the original factors must be 0. It's impossible to have two non-zero numbers multiplied together and you get 0 as a result. You have to have 0 as one of the two factors. So that means that either x is 0 or 1 plus x is 0. These two factors individually can be set equal to 0. This one's already solved, so 0 is one of the numbers you can't plug in, right? If I plug in a 0, the bottom is 0. And here, if I were to subtract the 1, I'm running out of room, subtract the 1, you get x equal -1. That's the other one that's excluded from the domain. If you were to plug in -1, you get -1. -1 squared is 1. -1 and 1 makes 0. So that makes a denominator of 0 also. And so to write out my domain, I probably would go with the set form on this one. And I would say that it is x such that x is not equal, whoa. Getting ahead of myself here. Not equal to 0 or -1. And I can put those kind of together in the same sort of equation there, okay? So that's going to be my domain. Okay, now let's look at another relation. This is a relation, right? But it does happen to be a function. And I could even put it in function notation, right? F of x equals 5 over x plus x squared.